Okay, let's dive into this. Welcome to The Explainer. Today, we're exploring an absolutely massive, game-changing shift in how we manage industrial safety and asset integrity. We are talking about integrating predictive AI diagnostics into industrial pressure vessel safety integrity audits. I know that's a mouthful, but essentially, for decades, the industry has relied on standard scheduled inspections. Now, we're using neural networks to completely revolutionize industrial safety, shifting away from reactive, fix it when it breaks, repairs, to a totally predictive, AI-driven model of integrity.
So, let me ask you this. What if you could see a catastrophic pressure vessel failure weeks or even months before it actually happens? It sounds a bit like science fiction, right? But honestly, it is rapidly becoming our engineering reality. You see, traditional hydrostatic testing only tells you if a tank is holding pressure today, but hidden subsurface fatigue, that's a literal ticking time bomb. The incredible power of predictive neural networks is that they allow us to see the fuse burning long before the explosion ever happens.
And look, the stakes here are anything but abstract. They are critical. Just to put this into perspective, a jarring 45% of all major process incidents investigated by the U.S. Chemical Safety Board between 2015 and 2022 involved equipment degradation. 45%. This basically proves that old methods of simply waiting for scheduled turnarounds are leaving facilities dangerously exposed. Moving right along to part one, the high-stakes crisis, focusing specifically on hidden subsurface fatigue. To really grasp this immediate operational threat, we have to understand the silent killer of pressure vessels, stress corrosion cracking, or SCC. It's a highly unpredictable, totally nonlinear degradation mechanism. It basically just needs three things to ruin your day: tensile stress, a corrosive environment, and a susceptible material. And the truly terrifying part? It's notoriously difficult to detect with conventional ultrasound testing. It just sits there, like a hidden threat lurking in your system. Because the real threat accumulates silently in those 12-month gaps between your manual API 510 and API 570 inspection cycles. Think about it. If you're relying purely on static, scheduled inspections, you're basically just guessing what happens to your asset between those audits. The degradation certainly doesn't pause just because the inspector isn't there, right? It progresses in the dark. Which brings us to part two, the tech-forward visionary, focusing on the rise of digital twins and AI diagnostics. And this brilliantly illustrates exactly where the industry is heading. The era of manual ultrasonic gauging is rapidly evolving into the age of the digital twin. On one hand, you've got the outdated manual review, relying on static API tables, waiting 12 months and digging through inconsistent spreadsheet logs. But the new AI-assisted method, it introduces facility-specific machine learning curves. It uses continuous Bayesian updating, meaning every single new piece of sensor data instantly refines the model's accuracy. We are literally transitioning from guesswork to absolute precision. Now, to actually feed those AI models, you obviously need incredibly advanced data. That's where phased array ultrasonic testing, or POUT, comes in. It captures acoustic emissions from subsurface anomalies. We're talking about advanced sensors physically listening to the exact acoustic signatures of a vessel under stress. By layering predictive AI right over standard safety audits, these sensors feed continuous streams of data into neural networks, allowing the whole system to identify microscopic structural patterns that human inspectors simply couldn't ever detect on a standard visual pass. Now, what's really interesting about this slide is the sheer scale of what we can see. These metallographic sections reveal microscopic, half-millimeter subsurface contact fatigue cracks. Notice that these are entirely subsurface. They exist long before any spalling or pitting actually appears on the outside. During durability testing, the AI successfully tracked these tiny anomalies continuously. It identified the exact failure point before it ever breached the surface. No way human eyes catch that. So all of this data fundamentally powers the digital twin. If you aren't familiar, a digital twin is essentially a physics-informed computational model of your pressure vessel. But the absolute magic here is the live sensor feed. You see, a static analysis only calculates stress at design conditions, whereas a digital twin recalculates the exact remaining useful life in real time. If your vessel experiences a random pressure or temperature spike today, the twin instantly updates the degradation trajectory across all affected circuits. It's like having a living, breathing model of your equipment. And the specific capabilities of these machine learning models are just wild. This isn't theoretical whiteboard stuff, this is highly deployable engineering. We've got convolutional neural networks processing thermal images to detect corrosion under insulation with over 87% accuracy. You've got supervised regression models predicting uniform thinning within a crazy tight margin of plus or minus zero point 0.3 millimeters per year. And those recurrent neural networks, they're out there flagging susceptible SCC circuits 60 to 90 days before a conventional schedule would even trigger a basic survey.
All right, let's look at the business side of this in part 3, the efficiency specialist. Let's talk predictive AI diagnostics ROI.
Because look, it's time to stop wasting millions of dollars on unnecessary maintenance shutdowns based on pure guesswork and rigid schedules. If you care about the bottom line, you absolutely have to look at compliance. And the beauty is, AI doesn't break the rules. It actually automates the traceability you need. For ISO 55000, AI provides an automated traceability chain. For API risk-based inspections, it handles real-time Bayesian updating for probability and consequence of failure. And for ASME PCC3, you get AI-generated remaining useful life triggers. It basically ensures global compliance by making your documentation seamless and completely audit-ready at all times.
So the crucial point is that AI does not replace the API-authorized inspector. Honestly, the certified human inspector is still the ultimate decision maker for fitness for service determinations. What AI actually does is empower them. It completely offloads the massive, tedious burden of cross-referencing code clauses and reconciling repair histories. It does all the heavy lifting on the data side, so your highly trained inspectors can spend their time, actually inspecting.
And when you empower your team with preemptive modeling, the operational impact is massive. Looking at this hard data from Siemens, leveraging predictive maintenance yields an incredible 85% reduction in unplanned downtime. By knowing exactly what needs fixing and exactly when, you're seeing a 55% boost in workforce productivity and a massive 40% cut in overall maintenance costs. This shift to preemptive modeling guarantees rigorous safety standards, all while completely optimizing your operational uptime through precise real-time data. It's a total win-win.
To bring this all together, this shift really does guarantee rigorous safety standards while optimizing your operations. As the industry consensus beautifully summarizes, we are integrating AI diagnostics into pressure vessel audits to pinpoint exact failure points before they manifest, ensuring global compliance while maximizing the lifecycle of your most critical industrial assets. It really hits the nail on the head. So I'll leave you with this provocative question to consider for your own operations. Will your facility continue to run on guesswork, or will you embrace the age of the digital twin to guarantee asset safety?
Like, share, and subscribe the channel for more videos. Language, English, India.